And unlike last week, we do have our speaker here on time and ready to go. I'd like to introduce Grégory Schueren. I hope I said that right, Grégory. And he is going to be talking about TCPSnitch, which was a paper that I read from a recent conference and I thought was pretty cool. And I hope that everybody else likes this topic as well. So I'll turn it over to you, Grégory.
Yes, thanks, Jason. Yeah, thank you for having me. Maybe let me introduce myself briefly. So my name is Grégory Vander. You almost got that right. I know it's a long name. So I come from Belgium. I'm 27. Currently, I'm a R&D engineer for TSRS, which is a company based in Belgium. And we offer a hybrid access solution to ISPs. So we basically have a software solution that allows them to combine multiple access networks, such as a DSL network and LTE network, to provide better connectivity to their customers. And we are using multipass TCP to do that. So that's about my daily job. So this talk is about TCPSnitch. So it's, as you said, a research project that tries to understand how the socket API is used by network applications. So to give you some context, it's a research project I worked on about a year ago now, I think. And this was actually the subject of my master thesis. So at the time I was doing a master degree in computer science in Belgium. And so I've done this work under the supervision of Professor Olivier Bonaventure and Quentin de Coninck, who is and who still is a PhD student of Professor Bonaventure. So I'll mostly reuse the slides from my thesis defense, and if you have questions, don't hesitate. I tried to answer them to the best of my ability because it's been quite a while now, so my memory is gonna be challenged here. So I suppose most of you are familiar with the socket API. So it's an API to communicate with the TCP stack on a system, and there's this central concept of a socket. So a socket is basically an abstraction that represents one of the endpoints of a network communication channel. And actually, we operate a socket much like a file. We can open and close a socket and read and write to a socket. So the socket API consists of a set of system calls to operate sockets. What about its usage? So nowadays, it's considered by many as the default API for connecting to the internet, and it's available virtually on every Unix system. And it's actually quite old because it originated in the early 80s, and over the years, it has evolved. New features have been added, but the current API still looks very similar to the original one. And on the other hand, the computing environment in which it's being used has dramatically changed. For instance, it's now being used on smartphones, tablets, embedded devices, devices that did not even exist when it was first created. And nowadays, many developers do not interact with the socket API directly anymore. They interact with higher level abstractions and frameworks, for instance, HTTP libraries, and you don't really see the socket API when you program. So this raises many questions. For instance, is the socket API still suited to support modern applications? Did some parts of the API become obsolete over time? And to the best of our knowledge, there's a lack of empirical data to answer these questions. So very little work has been done to investigate how modern applications use the socket API. And with this work, that's why, our intention was to start looking at this. So a brief outline of this talk. I will first explain you how TCPSnitch works. Second, I will show you a short demo of the software itself. Then I will cover the dataset that I gathered with the software. And then I will talk about some findings when looking at the datasets. So what is the LD preload trick? So there are two ways for an application to make system calls. On the right path, the application invokes the system call directly. So this is tedious, because the application has to take care of all the low-level details, and it's also non-portable because it's architecture specific. So on the left path, most often than not, application invokes system calls with library functions, wrapper functions that are defined in the standard C library. And these wrapper functions, they offer a programmer-friendly interface to invoke the system call. And these library functions, they are often dynamically linked with applications. This means that the library code is not included into the final executable. And when a process starts executing, it is the role of the dynamic linker to load and link the shared libraries that are needed by the application. And of course, an executable may depend on multiple shared libraries. And in this case, they are linked in a given order. For instance, here, libpcap was linked first before libc, and that's why I put it on top. So why does the order matter? Because if multiple libraries define the same symbol name, so the same function, the definition in the library that was loaded first will actually apply. So let's get back to our original example, where the application only depends on libc. Now, an interesting feature of the Linux dynamic linker is that it has the ability to link user-specified shared libraries before the regular dependencies of a program. This means that we can load libraries before libc. And that's exactly how TCPSnitch works. So this feature is controlled by the LD preload environment variable, and it may simply contain a list of user-specified libraries. And as a result, any function that is defined in such a library would take precedence over a function defined in libc. So with TCPSnitch, we just added a layer of indirection. We inject our library using LD preload, and then we intercept some system calls, some library calls. And we perform our own processing, and then we call the original libc implementation. So actually, this process is completely transparent to the end application. So yeah, that was how it works. So this looks complex, but it's actually very simple to use TCPSnitch. It's a command line application. In practice, it runs a command until it exits. So it's very like TCP dump, for instance. As shown on the slide, you can simply type TCPSnitch curl google.com. And basically what happens is that for each internet socket that is opened by the application, it will intercept all function calls. And for each function call, it will collect various information, such as the parameters that are given to the function, the return value, the timestamp, the thread ID, the error number, etc. And then it will bundle all those socket traces together into an application trace, which will also include some metadata about the system, for instance, the kernel version. And then it bundles this application trace and it sends it to a public database, which is available on tcpsnitch.org. And as you can see on the slide, it inserts to you with the link where you can access the trace. So tcpsnitch.org, it's a website, it's an open source platform as well, and it's really designed to centralize and visualize the traces. And as you can see on the screenshot here, upon uploading a trace, you have multiple metrics and charts that are computed automatically on the trace. And the goal is really to allow to get a better understanding of the network footprint of a given application. And you can navigate the traces and get statistics at different level of granularity. So first you can get statistics for the entire application, or you can get statistics for a given process within an application, because TCPSnitch will follow forks and it will then group information for each process. And then within the process, you can also view statistics about a given socket, for instance. And then on the homepage, users can also visualize statistics about the entire dataset or a segment of the dataset. For instance, you could be interested in seeing only statistics for the Android applications or only for TCP sockets. So the goal of this platform is really to be open, and yeah, everyone is invited to contribute traces. There's an option in TCPSnitch to disable the automatic upload, but the goal is really to grow the dataset. So let me maybe show you a short example of running TCPSnitch. Jason, can you see my terminal? I guess yes.
Yes, we can see it.
So as I said on the slide, just hit TCPSnitch, call google.com. So just to be clear, this is not my, I'm doing the video conference on a Mac, but this is a Linux machine here. I'm on a virtual machine. So it's running on Ubuntu 16, I believe. So here we can see that the curl succeeded, and it uploaded the traces, and it gave us the URL to the trace. So I'm going to share back the Chrome tab and maybe hit. So now, yeah, here we are on the TCPSnitch homepage. So in the overview tab, here we have statistics about the entire dataset. So we can see the function calls, the function usage, the number of traces and sockets, and we can look, for instance, at the sockets that were opened, the functions that were used, with the number of bytes that were sent. There's a lot of information. You can have a look, and then here we can browse all the traces that were uploaded. So here we have the curl trace that we just did. And below, maybe more interesting, for instance, a Firefox trace. Here on the trace homepage, we have the statistics for the entire application. Then if we hit process traces, we can have a detailed view for each process. So we can see it spawned 6 processes. Let's have a look at the first one. Again, we have statistics at the process level. And then we can see all the sockets that were opened. And we can look at a given socket. For instance, here a TCP socket where we had 300 calls. Same thing, statistics, and we can also see the individual calls on the socket. So here you can see the information that TCPSnitch is collecting. For instance, the error number, if there was an error, the return value, the thread ID, the timestamps, and the arguments passed to the socket. So yes, that's about the website. There's a tab to upload the trace manually, but normally you don't have to use it because it's done automatically by the software. So let's get back to the slides. So what about the data set? So using TCPSnitch, we recorded traces for about 135 applications, I think. And currently it only runs on Android and on Linux. So we have 90 traces on Android and 45 on Linux. And we basically manually interacted with each application for a few seconds to reproduce a typical usage. So in total, we tracked interactions with 24,000 sockets and about 5 million calls. So the Android dataset is mainly composed of highly popular consumer-oriented applications from the Play Store. So for instance, Facebook, Netflix, Chrome, Spotify. And at the moment, it does not include any server-side application. So that would certainly be interesting to add these, to have a look at several applications. And the Linux dataset is quite a bit different. First, it's smaller. It's only 45 applications. And then it's not really end-user applications. It's mainly composed of command line applications that are used by computer scientists, such as curl, git, or rsync. Then we also have a few specialized networking applications, such as dig, traceroute, nmap, and then a few traditional end-user applications with a graphical display, such as Firefox or BitTorrent clients. And also a few toy programs that I will present in a minute. So now let's turn to some results. The first thing that we noticed was that the API usage on Linux and on Android is very different. So this figure shows the percentage of applications using each intercepted function on both platforms. So in blue you have Android, and in yellow you have Linux. And looking at the picture, we clearly observe major differences in the usage of individual functions on both platforms. So more globally, we observe that about a dozen functions are used by almost all applications on Androids. Those are highlighted in red here on the slide. And for Linux, things are slightly different. Only 5 functions are really widespread. So in general, we realize that Android applications, they appear much more homogeneous in their API usage. And it's not only for functions usage, but it's also for socket options and other things. And for this reason, we believe that both datasets deserve to be analyzed separately. And we will see later that high-level frameworks and libraries really drive this API usage. And this partly explains these huge disparities between the two platforms. Because while on Android, application must use the Android SDK, on Linux, application have much more freedom when it comes to choosing frameworks and libraries to interact with the network. So the second finding was that the API usage, as I just said, is driven by high-level frameworks and libraries. And to demonstrate this point, I wrote 5 toy Linux programs, and they all perform the same simple task: an HTTP GET request over TLS for the same file. And then I also compare that with the curl program. So in this table, I contrast the API footprint of those programs on some chosen dimensions. On the first line, we have the number of API calls, and we can see huge disparities already. We can see that the JavaScript program only made 100 calls, while the PHP program made about 900 calls. Looking at the byte received, we also see that the Ruby program stands out. Actually, it's the only one that uses HTTP compression by default, and that explains why, at least at the socket API level, we saw less bytes coming in. And even on the most often called function, they don't agree. Most programs use read, that's not surprising, but then another use receive or file control. Looking at the socket options, it's the same thing. They all use one socket option, exactly one actually, but this socket option differs. And we also observed that some programs use the socket in asynchronous mode, while others use it in synchronous mode. And even when they use it in asynchronous mode, they don't use the same function to poll the sockets for data. So really what this shows is that there's no standard way of doing things, even for a simple HTTP request. A third finding was that on Android, the actual API usage is very, very different from textbook usage. So this graph is the same as the previous one, except that we have the function usage only for Android this time. And looking closer, we can see that all applications on Android use functions such as getSockopt, setSockopt, or getSockName. And those are not the first functions that you learn about in networking classes, right? And then we also saw that 95% of our Android client application use bind, which is a textbook server-side function. So that also surprised us. And here it's another perspective on function calls this time. So the previous graph was showing the percentage of application using each function. And this time we show the number of calls. So in blue, we can see that we have many reads. It's actually reads, receive, and all this family of functions. That's not surprising. In green, we have poll and co, also not surprising. And then in green, we have, in red, we have getSockopt. Alone, this function accounts for 9% of the function calls on Android. And that really surprised us. So then we had a look at the socket options that were being used. So this graph shows the socket option value that was passed to these functions. And we can see in blue that 79% of these calls use the receive timeout socket option. And in green, TCP Info. And I will get back to that later. And so we started digging the traces a bit more to find explanations for this behavior that we did not expect. And we quickly found some recurring patterns of interactions, especially at the opening of TCP connections, so on TCP sockets. So the pattern that is shown on the slide here was actually observed on most TCP sockets on Android. And it actually shows the observation that we just made. So we can see set sock opt, receive timeout, the socket option, we can see bind, file control, and in the text, in the paper, I will give a link at the end. We actually explain where most of these calls come from, so from which libraries and why they're being done. But looking at the trace, really where we can say that many calls seem redundant and wasteful. For instance, here, if you look at the bottom, we can see that we have two get sock opt calls, one after the other, and we saw that on almost all sockets. So that's one example of redundant calls that we've seen. Another finding was that on Android, UDP sockets are mainly used as a shortcut to retrieve information about the network configuration. And so actually, only 6% of the UDP sockets were used to exchange data. So you can see that in blue, 85% of the opened UDP sockets do not send or receive any data. The only thing they do is retrieve information about the networking environment using the ioctl function. Then in green, we have a lot of sockets that connect, but still do not send any data or receive any data. So again, that was a big surprise for us. And finally, a last finding was that TCP Info is really widely used on Android, and already mentioned that earlier. So it's TCP Info, it's an option that exports to the application counters that are maintained by the TCP stack. So for instance, you can get information about the congestion window, for instance. And so we already saw this graph. It shows the socket options that are being used in percentage. And we see that TCP Info is the second most often used function. And what is surprising is that the standard Java API on Android does not even expose this socket option. So that means that applications, they have to use a C or C++ library to use it. And still, it is used by about 30% of the applications on Android. And what we noticed is that usually this socket option is used only once on a given socket, except for 3 applications. They were all Facebook applications, so Facebook, Messenger, and Instagram. And what we noticed that for these applications, the number of TCP info calls is actually, it seems to be a linear function of the number of receive calls. So we know that they retrieve this option, but there are many information in there, so we don't know exactly how they use it. But it means that there must be some smart logic in the application that somehow make use of this information. Yes, so that's it for the main findings I wanted to share. On this slide, I summarized some. So I'm not working actively on this project anymore for about a year, but some things that I would like to see in the future would be to port TCPSnitch to other platforms. Because at the moment it's only running on Linux and Mac OS and Android, sorry. And Mac OS has a system similar to LD Preload, so we could port it to this platform. Of course, we could expand and analyze the Linux dataset, which is very limited at the moment. I think we could apply some data mining algorithms on the dataset to find more information, because here it was mostly by manual inspections that I had to look at the traces and compute some basic statistics, but I'm sure we can find more stuff in the data. And also what I wanted to do, and I did not have time to do, was to analyze traces for application in in bad network environment. For instance, when application lose network connectivity or where the latency is bad, just to see how they react and what they do in these conditions. If you want to get more information, the code for TCPSnitch is open source. You can find it on my GitHub page, github.com/GregoryVDS. So here you have the TCPSnitch repository. There's a summary of how it works, what information it collects, instructions to compile it, instructions how to run it on Android. It's a bit more complex, and yeah, that's about that. There's also a paper that Jason mentioned. I think you can find it on my GitHub too. If you are interested to get more information, yeah, it should be there, paper. And there's also my, if you're really interested, yeah, there's my thesis that you can read with more information. You can find it by typing the title on Google. I think it's the first link. The second link. Yeah, the page is in French, but I'm sure you can find the download button here. So yeah, that's about it. That's what I wanted to share.
All right, well, thank you so much for presenting that. Really interesting work. I've jotted down a couple of questions that I'm going to ask you. Others, please use the chat room and we can ask some questions of Grégory. I think the first one that I'm most curious in is, you pointed out that you've discovered patterns, and they probably relate back to the use of certain developer platforms and frameworks that people have used to do things either on Linux or Android. If you had to say, what is sort of the worst bad behavior that these platforms are contributing? Is it sort of that thing that you were pointing out regarding the use of blocking and non-blocking? Is it the abuse of TCP info? I mean, what do you think is sort of the worst abuse that you've seen with application development, looking at the limited set of data that you have?
Yes, one of the abuse I remember was the usage of receive timeout, because receive timeout, it's obviously to change the receiving timeout on a socket, and I believe it is not useful on a socket if you don't send or receive data, right? And I have the numbers is in the paper. I don't remember exactly, but I think that on Android, 30% of the sockets of the local sockets, so 30% of all sockets that were opened for TCP did a set socket option receive timeout, but they did not send or receive any data. So I could not find a valid explanation for that. It seems wastefully useless for me, but that's one that stands out. And also that many sockets are used, and for instance, the UDP sockets, 85% of them do not send or receive data. That also surprised me. It's actually showing that the application are using sockets for, maybe it's showing needs that application have that are not answered by the TCP stack. Yes, it's answered, but it's probably not answered the right way. And to get information about the network, that was really surprising to me.
Okay, and yeah, I was going to ask about the UDP thing second, so thanks for addressing that. So Eric has submitted a question. He's curious, what type of actions are you thinking of taking with regards to changing or improving TCP stacks after you were able to do the data gathering and analysis?
Actually, I did not go so far. As far as that. When I stopped working on this, I was still looking at the data set, trying to understand what was going on, and I did not really take time to think about recommendations or new abstractions that we could design for the TCP stack.
Okay. And Brett wants to know if the data sets are public. I believe you said that these are available on tcpsnitch.org.
Yes, all the traces are available on the website. You can browse the traces. You can, if you can browse them with the web interface. I think that's the easiest way, but you can also download them to have the raw files. It's encoded in JSON format. If you want to process them for something, you can download all the traces. There's not an option to download the entire dataset in one shot, but you can download in each trace individually. It's completely public, and actually the code for the web application is also open source. So if you want to improve it, if you want to do computation that are not available yet, you can modify the code, submit a patch, and I will no problem. I will upload it, and you can expand it to see other graphs, other visualizations, etc.
Okay. And have you had any contact with any of the applications that you were able to sort of model and give them any feedback about the usage?
Not really. The thing is that on Android, I think it's just we have so many layers of abstractions. Actually, it's frameworks of frameworks, and then in the end, you have the application at the very top, which is using the Android SDK, which itself is using other libraries, and in the end, it's just this. I believe it's just this. There are so many layers, and they're not responsible. There's not one of them that is responsible. Is the interaction of all these layers together that give these weird interactions. I remember that for the Facebook applications that were using TCP Info, I actually talked to a guy when I was in London last year. He told me that there's a library that Facebook uses in their application, and it's open source. You can find it on GitHub. I don't remember the name, but that's where the TCP Info calls come from. So I'm sure if we dig in this library, we can see precisely what they do with this.
Okay. So reminder for everybody, if you have questions, please type them into the chat. I sort of have one more. In the beginning, you were talking a little bit about sort of original intention of some of these libraries versus what we now see with some of the frameworks that are using them. You know, if you had the ability to sort of go back and give the data to the original people who designed these libraries, are there any recommendations that you would make to them to change things based on these behaviors? You know, the way that you see people using them now, is it any different than original intention?
I'm not sure. I think what we've seen is mostly programmer convenience. When we look at this pattern, of course there's a lot of redundant calls, but it's because these calls are abstracted away in functions that are being reused in the code all over the place. And in the end, if you wanted to optimize that, it would probably be a mess in the application code. It's just they have these utility functions that they keep reusing all the time. For instance, here you see. Can you see my mouse, actually, the cursor?
Yes.
Okay. Here you can see two consecutive calls, for instance, file control, and you can see that it's just that they have a utility function to change a flag on the socket. And what they do is that they first get the flags to get the current value, then they switch the flag that they want to switch, and then they write the flags. And of course, this could be optimized. You could remember the flags or just change a single flag. I don't know, but I think it's just for programmer convenience. And nowadays we have so much compute power that in the end, on a client application like the ones I investigated, I think it does not really matter that you make a few redundant system calls if it makes the application more maintainable and everything. But then maybe for server-side applications, then yes, it would be probably much more interesting to optimize these calls, and probably that recommendations would be much more useful to these applications.
Okay. Well, that was all the questions that I had. So I'll thank you again for giving us your time today, and we thank you a lot since we know it's late over there in Europe. If anybody else has any questions, please type them in. I'll make sure I post this recording. And we're going to take a 1 week break. We're not going to have a talk next week, but we'll have one the week after. So thanks again to everybody for joining, and have a good weekend, everybody.
Thank you.
All right. Thank you so much, Gregory. Bye.
Bye-bye.